Hello all, and welcome to TLT's webinar on basics of wear and wear protection. This is going to be the first of our multi-part series. We're trying to develop a webinar section of multiple different scenarios of wear and wear protection to give end users and industrial experts the knowledge and the experience that we've had in this department, so we can try to better equip the entire industry for understanding and for future developments of projects. Today with me is going to be Dr. Sebastian Fleeter. He is actually on the other screen as well. My name is Jesse Dravenstad. I'll be hosting the preliminary and the beginning portion of this webinar, and he's going to take over and discuss the scientific portion and dive a little bit more into the mechanics of wear itself and the wear protection. We are doing a live webinar shoot. If you have to leave, feel free. We're going to live record this, so then we'll be able to post this video later on down the road, so you guys will have a chance to review this again, and then also for others that weren't able to attend today. We're going to have a question and answer session, so please feel free to type in questions that you feel are necessary or information that you'd like to know. We'll try to answer a few of these questions towards the end of the presentation, depending on time, and then if not, we'll give you a direct answer back to you personally with whatever you need after that, after the webinar is completed. We're also going to do a poll around the end of it as well, just to ask where you feel and how you feel you're situated with wear in your current situations. So basically, we're going to do our best to explain some of our knowledge and some of our experience so you guys can get an understanding of where we come from and how everybody can work together in the future to start making fans last longer and protect them from wear in the future. So these are kind of a teaser for the next round. We're going to dive into 3 new topics after this webinar is completed. This one is going to focus on hard particle impact. We're going to look at basically rock dust and other hard particles, aluminum silicates, and things of that nature. And then for the future, we're going to look into water droplet impingement or high velocity water droplets. Doesn't have to be water, it can be any liquid. As you can see in the picture we have focused on the screen, this is out of a fan in India, and you can see the heavy erosion on the leading edge of the radial fan blade due to water droplet impingement. So it's a very serious thing. It shows up in some systems, and it's something to watch out for. The next topic we plan to cover in the future webinars is corrosion. We're going to do a lot focused on the actual fan components itself, but also some of the system components, seals and bearings, and other portions of the system. And then we're going to dive into caking and building up of materials. This kind of falls into sometimes the hard particle scenarios as well. So sometimes large buildups increase on your stator sections or your guide vanes or the fan housing itself, and these will actually break off, and these can be very dense, very hard buildups, and they can cause severe damage to fan blades. So it kind of falls into the hard particle at the same time it falls into a buildup. Now, all of these scenarios don't have to be individualized. They could all be working together. You'll have a chance that sometimes the liquid that is traveling through the fan system or the droplets are actually a corrosive, of a corrosive nature, and they also can be somewhat built up with dust and be sticky. So they could cake, be corrosive, and have water droplets associated with them. This also works with hard particle as well. So for this presentation, we're going to cover the content, typical examples of wear in different fans. We're going to cover axial fans, mixed flow fans, and radial fans. We're going to go into single and 2 stage for axials. We're going to step into a little bit of the theoretical background of particle wear. We're going to discuss angle of attack and densities and different materials and how things react. And then we're also going to go into some possible solutions. And we're going to talk about some different wear coatings and how they're best suited and how they don't always work in every single scenario for every single person. One thing we like to take away from all this is that everybody's scenario is different, every fan system's different, and a lot of times there's not 2 in the same. So, and if for an example on the right, as we talked about for multi-scenarios, which is why we're going to do the multi-session webinar on this, you can see that this fan, the rear nacelle portion covering the hydraulic unit, the actual stator vanes completely broke off. The actual whole nacelle section collapsed in the fan itself, and this was due to they picked up a high pH count in the fan system at prolonged mining. So they have rock dust and they have water droplet. They picked up a moisture content at the same time they have a high pH, and it aggressively deteriorated the fan portion itself. Now, these are all things that can be mitigated in the future with different materials now that they know that their mine is producing this kind of environment. But it just gives you a scenario how all things mixed together can really accelerate things. So we'll dive into the first portion of the fans. So we're going to step into typical wear on variable pitch axial fans. So as you can see, this is just a depiction of a power plant fan in the base of the screen. So you have your inlet box. So the air traveling in is the first stage of the fan. We're just giving a few definitions for people that haven't had a lot of experience around axial fans. The second stage would be the stage on the output side of the airflow going out of the diffuser, which is on this side. So what we'll show is the picture on the left is a depiction of the first stage of a fan system. So as you can see, you have your leading edge of your fan blade is the large red circle on the top, and you can see the concave cut into it and the heavy wear pattern, the brightening of the surface here. And you can see that this fan is experiencing a lot of wear on the leading edge. And this is very typical of the layout of a first stage of an axial fan. You'll see a large depression in the center portion here on the first stage. And then you're also going to see on the trailing edge a thinning of the material. So where it's doing a lot of the work on the pressure side, on the concave side of the fan blade, there's a lot of air pressure and a lot of the particles are starting to impact at an angle at that point. So a lot of material is going to be wore away from that individual area, and you can start to see the thinning of the material, and then it actually starts to fillet back or fold back. Now if we step to the second stage of this portion, you'll start seeing that the wear is pushed more towards the tip. So you're going to start seeing a decrease in material on the tip. These are, again, exaggerated pictures of examples so people can see, the drastic change in the fan systems. But you're going to see a lot of the wear generalized to the tip of the blade on the leading and the trailing edge. And you'll start pushing back towards the center. This is going to decrease the blade tip gap, which is going to lower the efficiency. And it's also going to decrease your ability to build pressure in the fan system. Now, another place that in an axial fan, a thick portion would be the hollow guide vanes. These are the vanes that are installed in the support structure for either the bearing setup or the motor or some of the tubing, which support, they protect the hydraulic hoses, lubrication systems, instrumentation, and so on. But they'll see an increased wear on the leading edge. They're wider than the rest of the guide vanes, so they get a lot more contact material. So you'll see a heavy increase in wear on the leading edge of those. This is usually designed out of the system. So what will be done is this is usually a heavier, thicker plate or a bar installed prior, and then the material for the hollow guide vane is attached to that, which gives you a long lifetime of wear in this hollow guide vane section. But there's also other scenarios that we'll see later that could be possible to help protect wear along this edge. Again, these are just depictions of standard wear and where you would look for it in typical fan systems. Something else that's also to be noticed, on axial fans, you'll get caking on the guide vanes or the hollow guide vanes or the nose fairing as well. So it's just a depiction that these buildups can come on the fan while they're wet. They come in at a decent velocity, they pack tightly, and then they'll dry out. When they dry out, sometimes they will break free, and then those large chunks will go through the fan system itself. So if a large chunk would break off and happen to be the contact point on a fan blade in this portion here on the pressure side, with that material being so thin, it can cause some serious damage. So another thing to watch is to look at your buildup as well while you're looking at wear inside of a fan system. Now, some natures that come with this, you're going to see that with this increased wear, you're going to lose fan efficiency. So as you lose blade profile, your pressure is going to decrease, which also is going to decrease your efficiency. Typically, on a normal wear of a fan system that's encountered, as the fan blades wear, you're going to drop your efficiency 3 to 5%. A lot of that's going to be relative to the tip and the blade's tip gap due to the wear, and then losing the performance of the pressure side of the rear fan blade. Now, you're also going to see a decrease in pressure rise. A lot of that has to do with the tip gap and losing a lot of material off the blades. So it's kind of a combination of both, but anytime you have wear in a system, you're going to lose efficiency and you're going to lose pressure rise. So you're either going to have to speed up your fan to compensate or make the blades more aggressive and start using more power. So we'll step into the next style fan, which we designate as G-type or an AN fan. This would be a mixed flow fan. The blades are welded to basically a conical rotor. And as you'll see, as the wear patterns are a little bit different than the axial fans. You'll start seeing, as the depiction on the left shows, this is the blade in reference, and then this is the leading edge of the fan blade where my laser pointer is going. And the highlighted square is this portion here. And what you're seeing is the erosive material, the media, has actually chewed through the whole leading edge wear protection, or the weld-on or the hardened material, and it's got into the base material. And what it's doing is it's channeling and grooving and removing the material in the leading edge of the fan blade. And as we look at this from this angle, not so bad, but on a further inspection, you can see that there's a lot of missing material. And we'll step to another angle and you'll see that it's even more aggressive. But then when you look at it from the back profile of the blade, you can see how much material is actually lost. So once it actually broke through the surface, it started aggressively working its way through this system. And as it's working, you can see where it's more aggressive here. It's a little bit less, but you can see that's working in a pattern down the fan blade itself. So as it's removing material kind of uniformly down the fan blade. Now, the picture on the right is a very severe case. And you can see that all of the leading edges are heavily eroded. And then you also see that a lot of the wear protection is eroded off the fan blade as well. And as you can see from blade 1 to blade 3 on this picture, if you follow my pointer, the first blade seems to have all of the tip still attached to it. Then you move to the third blade, and you can see that it's missing a large portion of the base material. And with that large portion of the base material, it's actually throwing the rotor out of balance. So something else to watch for on wear is the reduction of material to actually cause the fan to go out of balance. Now, axial fans aren't as susceptible to this. They will see more uniform blade profiles. The wear patterns will be similar on all blades, unless you have large particles or a blade gets to the point where it gets thin enough that it actually breaks off or damages or goes through another blade. And then you'll start to see more imbalances, but usually they wear pretty evenly. Now, the AN fans are very susceptible to imbalance. If you lose a large chunk here, it'll throw the mass of the rotor out, which will cause a heavy imbalance in the fan system. So, and as you can see, just in a zoomed in picture of this edge here, you can see how it's channeling on the outside on both sides, but also channeling all the way up the middle of the blade, which is causing the air pressure and the airflow and the media to travel into here, but it has to exit. So it's exiting out the tip and it's starting to work its way through the top of the meat of the blade. And that's where you see the large erosion up here on some of the fan blades. So for this style fan, you're going to see also the same as you would have saw in the axial fans. You're going to see a reduction in fan performance. You're going to see heavy erosion on the leading edge. And you're also going to see a lot on the trailing edge as well. But it's going to be mostly isolated to the pressure side. But as you see, since it went through the pressure side, it's actually built itself cavities, and with the little lips on the top here, it's chewing off the actual non-pressure side of the fan blade. So in summary, it's going to lower fan efficiencies, lower pressure rise, and an imbalance of the rotor impeller. So those are some typical locations and things to watch for on actual AN fans or mixed flow fans. So we'll step on to radial fans now. So you have your centrifugal fan, which most people are very familiar with. But where you're going to see the main wear on these is on your leading edges of the actual fan blades themselves. And then you're going to see it on the pressure side of the fan blade. So as you can see in the picture, the orange and the yellow is the depiction of wear plates or hardened material to be added on. And you'll see down in the corner here as the depiction of the leading edge of where it's going to be a lot of impact. And this is near the backing plate or the center plate, depending on if it's a double width rotor or a single, depending on whatever your definition is or what you've been told. But you're going to see a lot of wear here. The air is going to be traveling into the rotor, and then it's going to be pressed against that backing plate. So you're going to get heavy wear there. You'll also see it on the pressure side of you can see the wear plate here on top of this fan blade itself. And what's happening is the erosion line is coming down the pressure side of the fan in between the joint and the backing plate. And it's actually wearing through the weld seam and then working its way into a larger cavity on the trailing edge of that fan blade. And now we'll go to a little more aggressive to show you a little more depiction of how far it can go. So this is a scenario of a large wear groove inside a radial fan blade. So it's working its way through here, and it's actually chewed itself completely off of the mounting surface. And you can see it's been doing it for a long time due to the wide gap here. So it's still wearing on that actual fan blade on the edge of it while it's in operation. So this fan was still in operation, still performing. You're going to see a lack of performance, but even with only maybe 1/8 of the fan blade actually attached still to the backing plate, the structure of the fan was still sound enough to survive. So there's a lot that goes into fans that are going to be in erosive environments on the structural design and the allowances for blades to be deteriorated. Now, one way to battle against this is to use wear plates. So we're going to step back and forth between two slides here so I can show you a depiction of where a wear plate goes. As you can see, the orange and the yellow in here would be a depiction of where we'd put a wear plate. And the wear plate acts as a material that can be eroded over time to save the actual structural material of the fan itself. But you're going to see the same wear patterns on the wear plates as you do on the fans themselves. So as you can see that the wear plate has a lip brought up along it to give itself basically an extra protection against the backing plate. So this would be your leading edge, and the media in the air is going to travel over the pressure surface here. You're going to get a lot of wear in the center, same as what you saw in we're going to step back 2 pictures, same as what you saw right here, the development of this area in this section. And this is going to be thinned out, and then it's also going to travel along this line, and you're going to see a large loss in the leading edge and on the main surface. And then it's going to start cutting its way into the trailing edge. So you're going to see that it's going to start grooving in different patterns in the trailing edge depending on the airflows with the wear plates in the system. So design, layout, and whatever, and the way the fan system's moving the air plays a large role in where the actual isolation of the wear goes in the fan system. Now, Sebastian is going to step into a little bit more on the mechanical side of particle impact and different scenarios, different angles of attack of the particles itself. So we will bring him on, and he will step into the next section.
Well, thank you, Jesse, for the introduction. I'm going to sort myself a little bit here, and I hope that this sharing is working all right. Well, before we get a little bit scientific, I'm going to show one example, which is a radial fan with wear protection in a fiberboard production plant very close to our site in Germany. So in this plant, they use wood to chop it down to chips and make it to those fiberboards you can see in this picture. And all the waste of this production goes into a power plant to generate the heat and the electricity needed to produce this. So, This is a picture of this fan they are applying there. And all those wood chips that are used in the burning, they contain a lot of aluminum oxide, which is a very hard particles, and a lot of sand, which are very hard and very large particles. And those particles are going to hit the fan, and especially what you see here, on the leading edge of your fan profile, the structure here, which you can see is quite damaged by those little lines here. So what we did there was simply to apply some wear caps, so to produce a cap which could be mounted to the fan by some screws to the backing plate. And this wear cap was once again protected not only the base material, but with an additional layer of a thermal spray coating, which is called TLT-H101, and it's a chemical composition which is developed by TLT-Turbo and some sub-suppliers, and they have a very high hardness. So this cap could protect the fan very good. And before, they had to change the wear protection and re-weld on the fan after a time of approximately 5 months. And now, 5 months later, what you can see with this wear cap is only the small crack in the welding area here, which is marked in yellow, and all the rest of the leading edge of the fan blade is still intact. So this is one way to protect the fan, but another one is also thinking of a design change, because every wear protection measure we are taking is only fighting the symptoms, but it's not fighting the root cause. So what we need to think about is also having design change, like in this case, perhaps changing to a larger impeller at lower rotational speeds. So you will have the same pressure rise you will need and the same volume flow, but you will have decreased velocities at the inlet. Therefore, this will benefit on your wear protection. So now we get a little bit more scientific. So theoretical background, what are the main influencing factors for wear? First of all, it's particle velocity. So the velocity of your wear particles in the gas stream. It's also the shape, it's the size of those particles. Size, density goes together to energy, so the energy the particles are transporting. But it's not only that, it's also the impact angle. So if they are hitting straight or if they're only touching a little bit. It's also the hardness of your particles and the hardness of your base material or your wear protection. And also it's particle mass flow. So every particle transports energy. The higher your mass flow is, the higher your total energy is. And also not obvious on the first look, but the temperature. If you're operating at very high temperatures, then your base material or your wear protection may also change in its performance. And therefore, the operating temperature is very important to know. To evaluate all of those influencing factors, we have a test stand at TLT-Turbo, which is depicted here in a CAD model. You can see on the left picture, there's a feeding path where we can feed in some abrasive media, which is going into a nozzle, and the nozzle is operated by pressurized air. So we get a pressurized air and abrasive media stream coming out of this nozzle. We have a holder here, which is turnable, which holds a plate of the base material or coating or whatever we want to observe. And the nozzle is shooting the particles on this plate. And with different tests in different time frames, we then calculate an erosion rate, which means how much of our material is lost by shooting the particles on it, and how much particle mass do we need to shoot this away. The same can be done for a volumetric erosion rate, which is then simply calculated by the density of the base material. because you're not interested in how much mass do I lose. You're interested in how much volume is still there on my blade or on my disc. And most important for us is relative erosion rate, which means if you have an erosion of one material, you can compare it to other materials by simply dividing it through each other. We then get those little nice diagrams you can see on the top here. You will see those diagrams a lot more in the following slides. We always depict erosion rate on the y-axis and our impingement angle on the x-axis, and then we will see different lines. This one is a high-speed video, 35,000 frames per second of the particles in flight at our test stand. The particle velocity here is approximately 180 meters per second. Important to know, the particle velocity is not equivalent to the air velocity because the air is not transporting all of its energy to the particle. In this case, it's quartz particles, 200 micrometers in size. And we can have a look at this little video. You can see the nozzle on the left side, and those little white balls shooting out of the nozzles are the quartz particles hitting our plate here on the right side and bouncing back. And with every bounce they will take a little bit of material with them. So if we now observe different impact angles, we observe different kind of wear and different microstructures behind it. In total, there's 4 which are important for wear in fans. One is microploughing, depicted here on the left top, and microchipping. Those are called abrasion. Abrasion means we have a very low impact angle, and they simply groove in, take a little bit away, which is the case when the impact angle is lower than a critical impact angle. And as soon as your angle gets a little bit steeper, you go from grooving to chipping and cutting, and then you really it's on a higher scale that the deformation of your material takes place. We can see that on a microscope picture here from an aluminum sheet, which was irradiated by quartz sand. And there's one particle which chipped out something of the material, which you can see here. So the particle hit here and chipped out something of the material. You can imagine when this happens several thousand times per second, there's a high chance of really getting away the material. The other one is more erosion part. In this case, erosion, we have a very high impact angle, very close to 90 degrees. So it's hitting straightly, directly to it. And there it's more crushing and fatigue mechanisms that damage your material, which can also be seen here. Sometimes even the little quartz particle gets stuck in the base material and need to be washed out again. So what are now different wear characteristics? Here is one of the diagrams I talked about, erosion rate and impingement angle. Wear does not equal wear. It's very important to observe it with the material you are looking at. So if you have a very ductile material, aluminum, structural steel, you will have an erosion rate at very low angles. It will rise a little bit to a maximum and then drop down the steeper your angle goes. Whereas when you have a composite material, it's, for example, very hard particles in a ductile matrix, for example, spray coatings, thermal spray coatings, you will have more a steeper rise to the maximum and then a drop down. And when you have very brittle materials, you will have higher resistance and lower erosion rates at low impingement angles. And then a rising to until we hit the 90 degrees here. These are, for example, hard facings, weld overlays, something like this. Okay. Second one is also the velocity. So when your particles hit the surface with a velocity of approximately 100 meters per second, you have a very low wear, very low erosion rates. When you increase it to 200 meters per second, it rises, 250, it rises even more. And what we can observe is velocity does not go in linear, it's more to the power of 2 or to the power of 3. So doubling your velocity means 4 to 9 times higher erosion rates. Also influencing factors are particle size, particle shape. So in the particle size, we have a very high erosion rate for large particles. And the smaller your particles get, the lower your erosion rate will get. This can be simply explained by the kinetic energy the particles are transporting. A large particle at the same velocity will have a higher kinetic energy to hit your base material and damage it. But also the shape is very important. So when you have very sharp particles like those one here, they will have very high erosion rates for your fan, whereas more circular or egg-shaped particles will not damage your material as much as the sharp ones will do. So it's very important to really know what abrasive media are you using in your fan, to have a deeper look on how the erosion in your fan behaves and what can be done to help against it. A very important factor is also the different hardness ratios. So when we observe particles with the same kinetic energy hitting a base material, we can calculate the particle hardness divided by the material hardness, which will be depicted on the x-axis here, and the y-axis is once again erosion rate. We are observing low impact angles now, and when you do this with different material, structural steel, aluminum, hard facings, thermal spray coatings, you will find two different behaviors, one for very brittle material, which is here in the red line, and one for very ductile material, which is the black line. Whenever you have a very hard particle and a very ductile base material, you will have a high amount of wear. But the interesting thing is, by reducing the hardness of your particle, the erosion rate is not changing very much. It stays nearly constant until you reach a factor of 2. So when the hardness of your particle is 2 times the hardness of your base material, the maximum is reached here. When you increase the hardness of your base material, the erosion rate will drop significantly until a factor of 1. So this means base material and particle have the same hardness. And then it will drop further, but not so much. So improving the lifetime of your fan, we will always search to get to a hardness factor of 1 or close to the 0. But we will always aim to be below 1. Because between 1 and 2, the increase is dramatically, and this will really change the lifetime of your fan. When we observe this for very high impact angles for the same material, there's a little different behavior. For low impact angles, very brittle materials are an advantage. They have lower erosion rates globally, whereas when we have the high impact angles, the lower or the upper shelf of the ductile media is lower than the one for the brittle ones. So having a lower constant erosion rate with those very ductile base material. Once again, there it's really, really important to have a closer look to the wear particles in your flow stream and the base material to really choose the right combination. So what are now possible solutions and what are TLT-Turbo's developments? You can see one case here, which is from a Canadian mine. They have a combination of rock dust, of a very low pH value for corrosion, and also water droplet impingement. And they had aluminum blades with a tungsten coating on it, and the tungsten coating was flying off because the corrosion was destroying the bond between the tungsten and the aluminum. Therefore, we switched there to titanium blades with a ceramic liner on the leading edge to additionally protect the leading edge. And with the help of those measures, we were able to make the lifetime of the blades very, very long. So they had to change the blades every 5 months before, and now they can operate much, much longer. But not only those protective coatings or base materials or wear plates, also general material selection or even aerodynamic design can be solutions, as already explained for the fiberboard case. So what is TLT-Turbo offering as coatings and base materials? Once again, we see here the erosion rate for different impingement angles. Our reference case in this one will be a structural steel S690, which is very often used in applications with wear for the fan. And we can have a look at different coatings, how they behave. TLT-H101 is one thermal spray coating with a chemical composition developed by TLT-Turbo. And we have very low erosion rates globally over the whole range of angles. So this should bring an advantage. When we have a look at another thermal spray coating applied by the same technology, but having a slightly different chemical composition, we see that this has higher erosion rates. So it's not only a matter of technology, how to apply a coating, it's also knowing the exact chemical composition and designing the chemical composition to your needs. H103, another thermal spray coating by another technology. You will see it here with higher erosion rates. And then we also have different kind of weld overlays like the W104, which performs pretty good at low angles, but is not very good at high angles. So that's the case I highlighted before, where at high angles, the ductile material like the S690 have advantages over very hard and brittle materials like the weld overlay. But also weld overlay is not equal weld overlay, so different kind and different technologies to apply it will show you different behavior. It also has an influence if you take it parallel or rectangular to your flow stream and many other things which you can see here. But all weld overlays share a similar behavior with low erosion rates here at low angles and rising until the maximum at very high angles. But sure, those are not the only options you have. We can also work with polymer coatings. Some of those polymer coatings can be easily applied and be repaired much better, like the P105, which is designed for TLT-Turbo. What you see here is that they are very good at high impingement angles. They protect very good against particles coming straight, but they have very, very high erosion rates at the low impingement angles. So what do we take from this? Every application, every fan, every plant, every system is different. There's not one like the other. And therefore, TLT-Turbo is not offering one wear protection. We are aiming in offering the optimized wear protection for your fan and for your plant. And how we are going to do that will be the part of Jesse. So I'm going to hand over the presentation to Jesse once again, so he can close our webinar. Jesse, I think you're muted.
I am. Sorry about that. I will start over. Sorry. Thank you, Sebastian, again, for going through the detailed portion of this webinar. Very good depiction of the mechanics and how the wear actually works. To recap just a second ago of my being on mute, we had one of the questions came in about how does this process go about? How can we do a tailor-made solution? There's lots of options. We can look at a generalization just for understanding. We're very good at just answering questions related to here's a certain scenario, here's a certain power plant, we have this kind of stuff going on, we're seeing this. We can help with that aspect as well. We can also dive into the very deep details. We can go into actually taking a dust sample or a material sample of what's going through the fan. We can look at the atmosphere environment as well and test what the chemical composition of the air and the moisture levels are. And then we can also look at basically the design of the fan system itself. Even if it's not our fan system, we can take it and replicate it and look at where air flows travel and basically how the air streams condense into certain areas to increase wear. Maybe come up with solutions on the design of that fan as well. This happens a lot with radial fans, being able to change the actual internal rotor and keep the original fan housing itself, and sometimes be able to change wear characteristics from certain stressful locations. So if we were going to follow the prospect of taking a dust sample from the customer, I mean, it can be provided to us. We have field service people that could take a sample on site as well. But a customer could ship us a sample, give us a scenario of their fan, the rotating speed, all of the relative information that we're going to need. Usually drawings and things of that nature help, even if it's just general arrangement, duct sizes, air velocity, and things of that nature. And most fan systems, everybody has that readily available. So then we can take that, we can analyze the abrasive, we can figure out what's in it. We can look at size, the magnitude of the particles. We can look at the aggressiveness of the particles themselves. Are they spherically shaped? Or are they jagged? And we can compare it to what the base materials are of that fan system itself. And then we actually have the opportunity to either replicate those samples in a glass media or an abrasive media, or we can actually have enough sample quantity to actually shoot the actual tested sample into a tested material that they're using with different wear coatings, or even the base material to get a scope and figure out what is the best plan of attack. So we'll use our currently installed test bench system, and then we'll test the materials against different plates and different base materials and different surface materials and different wear coatings as well, based on what we feel would be the best scenario to go with. So we're not spending a lot of time just testing all samples. We'll travel in a direction that we know is probably the right direction prior to testing all the samples. What that kind of gives us, we can get a real life scenario of what's going to happen. We can look at material thickness versus the fan's operating condition, the hours of operation, and what's happening, and kind of depict the life of the fan blade. Even to the point where if the system's modeled, we can figure out what the performance loss is going to be in the future versus the fan blades themselves. So basically that's how we end up getting to a tailor-made solution. Sometimes it has to do with a test bench, sometimes it just looks at the chemical composition of the environment, and you realize it's a very corrosive environment, so a material change is needed. So the environment will be based on the material. We'll design a material that'll handle the structural strength needed for the rotating equipment, and that becomes the new material in the fan system and avoiding the corrosive environment. With the abrasive, you usually have to follow the path of what is the abrasive and how is it contacting the fan itself. So real-time tests are very good. We are also able to run sample products. We've done it in several fans. You can take different coatings and different materials after they've been suggested and run them as test samples in the fan itself. So if a new set of blades is being installed, we can do opposing blades with a certain wear material and then opposing blades with a different wear material. And then that gives you a chance to run the fan through a normal life cycle and then do a real world scenario of how those materials act in the fan without causing any changes to the fan system or anything along those lines. But it gives you a chance to pick for the next round the exact right wear protection for the longest life you can get out of your system. So that process we go through a lot. We'll also look at fan blades that are brought in with certain coatings. We'll take test samples of the current coatings that are on those fan blades, and then we can look at the wear patterns that they're getting and see if we have something that would be better offered for that environment. So this is kind of the approach for how we go through this. And then another question we had is about how long this is going to take, and Sebastian will answer that in a little bit. So at this point, we'd like to do a poll. It's nothing super fancy, but it's just a couple questions. We'd like everybody just to, if they could, click on one, just so we can kind of get a depiction of where we need to focus. Like, do people need wear protection, or are they okay, or do they need reached out to? So if you guys could please complete the poll. We're going to give it a couple minutes here and see where we go. And I think Sebastian is starting it at the moment.
Should be running. I see there's already a lot of you participating. We experienced some problems later where people were not able to mark their choice. So if you cannot choose an option, you might end your full screen mode. If you have it on full screen mode, then it should work.
And while you guys are polling, we'll talk a little bit more about some of the solutions. Some of the stuff doesn't happen overnight. I mean, we might even work with a customer and end user over maybe 2 life cycles of a set of blades. Because I mean, you can look at the primary information. Usually fan blades are usually installed during that time period, so you let that cycle run out, and then you either try sample blades or you move on to the coating that you feel is we feel is the best solution for your system. And then that's what's actually going to depict your increase in life and the longevity of the fan system itself.
All right. We have already a lot of participants in the poll. I'm going to close the question now and display the result. And it's very interesting that almost half of you participants are interested in getting a tailor-made wear protection, or at least need more information on that. If you need more information, we can provide this. That's no problem. Either you contact us, we will show a contact information slide at the end, or we also have your login data from the webinar, so we will contact you afterwards to see how we can help you even more. And for the other 50% who say, no, it's not relevant for me, well, it's our turn to convince you that it is relevant for you. Nevertheless, thank you for participating in the poll.
All right, so I think we're back to a few questions. We'll step into those. We had one question about the, Sebastian has extensive time in the research department for materials. So he can kind of give us an answer of about how long the process takes from receipt of sample to maybe a selection of a wear coating.
Yeah. Well, the longest time should be, depending on where you are, is shipping time for your samples. But as soon as we receive the samples, the test should take place within 1 or 2 weeks. Then we are able to give a first recommendation or 2 or 3 recommendations, and then we have to discuss: is it more about lifetime? Is it more about value performance, which you're aiming at, or how we proceed? But it's a matter of a few days or weeks until you get a report, and then we discuss it. And then the longest time will be the lead time and delivery time for the wear plates and the coating itself.
And I think we have one more. I mean, there's another one just popped up. Sorry if I have to walk off screen for a second to get to the question. Okay, so the question is like, wear material for the AL203, is it a blend of materials, and how is that application applied? Sorry, there's a train in the background.
The wear material, basically, those wear materials are applied by screws, bolts, or you can also weld it in. And then you can exchange your wear plates. And when we're talking about the thermal spray coatings, it's all about the chemical composition of this coating, what the blend is, what the composition is. But especially as those thermal spray coatings are hard to repair on site, we are doing this on the wear plates. Whereas when you have a weld overlay, then you can easily repair it on site. Then it's easier. You can also apply it directly on the supporting structure of your fan.
Nice. All right, we've got a few more questions too. We can try to get through. We have a couple minutes left. One of the ones that just came up was the discussion of temperature variations being more corrosive or less corrosive. That's something we're probably going to dive into a little more heavily when we do the corrosion webinar portion. We'll dive into what which the question is 100% correct, that yes, temperature plays a big effect on the corrosiveness of the materials. So we'll probably push that one as one of the large topics in one of the next webinars coming up in the series. And then we had another one, hold on, so I have to step off screen for a second, talking about cost benefits versus the wear materials. Adding different materials onto a fan, we don't really have a graph to show which ones cost more in comparison, because usually that's not the end goal is to see which one's the cheaper benefit to put on. It's usually which one makes the fan last longer. If we can keep a fan up and running for an extra 3 years without any downtime and any maintenance, that's usually the cost savings versus the actual application cost. And then in different scenarios, when blades are being freshly manufactured to when set of fan blades are being repaired, the cost can be different in the coating procedures. So we don't really have a generalized cover over that one. And we've started to get a few more questions coming in, and we'll try to specifically answer those to the clients themselves. And then also, if anybody else has any other questions, feel free to keep asking them. We're going to step into a little bit, just move over to, we want to thank you for coming out to this webinar. Our whole goal is to be able to release our knowledge to end users and industrial experts. We want to be used as a tool. So anytime there's questions, anytime there's a misunderstanding, even like you're just trying to figure out, maybe this is a solution, maybe it's not, we're here to help. Like questions, I mean, we look forward to them coming in the future. No question's too small. It might not even be a job that you're actually making a change to, but you're just trying to understand something happening in your system. So there might not even be any financial gain for either person, but it's just for some more knowledge and some more information. We're happy to give that. So our contact information, so we're the host of today. And if you reach out to anybody for this webinar, we can get more emails and different people in different departments as needed. And then for contact information for wear protection or to get passed along to the right division group, we didn't want to do all of the global entities for all the locations. So global market is going to go through the European office, Jennifer Hoffman. So the email address is going to be service@TLT-Turbo. Any questions you have can go to her. For the North American market, for specifically if you want to just get direct contact, James Cushing is handling our aftermarket department, mostly power and industrial fans. And then Reggie Berry will be able to assist in mining. So it's r.berry@tltturbo.com. And if you guys need any more stuff, please feel free to, we'll leave this open till the end of the session. Keep asking questions or follow up with further questions, and we'll give you as much information as we can give you and try to push you guys all to the next level for longer life fans and longer life systems. So again, we want to thank you for coming out, and I want to thank Sebastian as well for presenting the technical portion of this presentation, and we appreciate all of your guys' attention.
Thank you. Stay healthy.